Hi, welcome back. In the last lecture, I said the 10th lecture may be the last one, but then I checked with ex- the video on continuity on metric spaces, and there I have proved only two equivalent conditions. Okay, because people ask for epsilon delta and sequential continuity, I explained that. But then I also want to include in terms of inverse images of open sets, etc. So we will have two more lectures minimum on this issue. Okay, I I think you're happy. That is okay. Let us start sharing the screen. See, before I forget, okay, even though I may need it only after about 20 minutes, okay, but let me just say something very important, which I forget. Usually I will do it earlier. Two things, okay, even in metric space, we talked about sequences and their convergence, right? There are two questions I want to talk about. Suppose I have a sequence xn which converges to x, okay, in the definition. Do you see that this is equivalent to saying the sequence of real numbers converging to 0? Is this clear to you? This is the first observation I should have made, but as usual, I don't come prepared. I just think, okay, well, when I start lecturing, so whatever comes to my mind, I do that. This is clear? Okay, let us quickly go through what does this mean. For every epsilon positive, there exists a natural number such that for every k greater than or equal to n, okay, what happens? It says that distance between xk and x is less than epsilon. Okay, this is equivalent to this. This is the definition, right? But when I say dx and x converges to 0, what does it mean? You are going to give me an epsilon. I have to find a natural number n so that for all k greater than or equal to n, distance between xk and x should be less than epsilon. That is what you have done. You understand? Okay, please make sure you follow this, because if you're a beginner, it's good to go through this. Don't simply accept it. Okay, many of you want to accept. Don't accept. Okay, I'm no god. Okay, so whatever I say is not gospel truth. You can question, and you have to understand. The third thing is, this is what usually I ask, but again I forgot. I don't know why. So suppose x in x is given, can you think of a sequence xn, okay, in x, so that xn converges to x? Of course, obvious choice will be take xn equal to x itself, and maybe it may happen, right? Yeah, but the and better way would be look at this x, okay, and suppose this is a radius 1, this is radius half, this is radius 1 by n. So what I can do is I can choose an element. I say although it is here, but it may be even here, like this. You understand this? What I that is, for each n, choose xn in bx1 upon n. Notice that if x is a discrete metric space, then if n is okay, then bx1 n bx1 upon n will be only singleton x, though my xn may turn out to be all the time x. That's a possible. But in general, okay, I can choose any arbitrary xn in bx1 upon n. Do you understand that? Now, is it clear that xn converges to x? Yes, of course, because distance between xn and x is less than 1 by n. And by my earlier criterion, xn converges to x. You understand this? What is very interesting, important, and significant to notice is, okay, suppose there are infinitely many choices for your xn here, bx1 upon n. For example, in the case of r, okay, I choose x and I choose x minus 1 by n to x plus 1 by n, then I could have chosen uncountable, there are many uncountable many choices of xn here. I could have chosen any one of them, You follow that? So there are so many ways of constructing a sequence xn now, but if I choose like this, my xn always converges to x. Isn't it something wonderful? Do you appreciate that? If you simply say this, it looks very prosaic, okay? Just, okay, nothing great. But think of it the other way around. There are lots of choice of xn for in the open ball bx1 upon n, like in this case. Okay, in this case, it's uncountable many if you know something about countability and countability. Okay, therefore, there are uncountably many choices of sequence xn, which can, okay, but no matter how you chose, all my xn will converge to x. Okay, keep this in mind. Okay, pause, review, proceed. The significance is, okay, for any choice xn in bx1 upon n, the sequence xn is converges to x. This is the significant point. Okay. Now let's go to the standard definition of continuity. Let me call it definition 2 in terms of epsilon delta. Many students have problem with the reason why epsilon delta, it looks very artificial, etc. It's actually not artificial. Okay. In my book, I would explain, and also you can look at my the Andhra Pradesh Academy of Sciences lecture. Also, I would explain this epsilon delta. So I will be brief. Okay. Please refer to my book or please refer to the video under FTV program of Andhra Pradesh Academy of Sciences. They are also explained. You see, suppose there is lot of input. This is your x. Okay. So this is a y. Okay. So what I have is this x, maybe a lot of components, like this may be actually like something like an Rn. Okay. X1 maybe something like a copper, and X2 maybe nickel, X3 may be steel, and so on, and X4 may be coal, X5 may be silica, X6 may be sulfur, and so on. It could be anything. So what I do is I have to take certain amounts of this, and my F is a scientific process. Okay, this is very precise process. So if I give the input X here, I will get the output Fx. Right? Now let us assume as a consumer, you want this output Y. Okay. So to get this Y, what I have to do? I have to put the precise X. Then the scientific process F is something it will produce. If I apply F, the scientific process to this ingredients, I'll get Y. But unfortunately, the scientific process is so precise, right? That all your elements X1, X2, Xn or whatever X should also be very precise. That is, when let's say X1 is copper, copper should be 100% pure. And X2 may be nickel, it must be 100% pure, and so on and so forth. Okay, if you have some kind of an idea of reality, nothing in the world is 100% pure. Okay, even if you buy a gold coin, they will say only 99.99% pure. Okay, you pay through your nose for a gold coin, but it will only be 99.99% pure. It's not 100% pure. So it's nothing is pure. Okay, so you know that, okay, I may not get Y. So what I do is how much of error I can tolerate. If my Y dash, okay, is very close to Y, that is the distance between Y dash and Y is less than epsilon. This epsilon you prescribe how much you can tolerate the error. Okay, then as a scientist, what I know is if I choose my X dash, which is delta distance, okay, then if I apply the scientific process to, because I may not be able to get X, but I may be make sure so whatever ingredient for F, it will be X dash, which will be delta precise to X. It will be delta close to X. Then I know Fx dash, scientific process is so nice that Fx dash will lie in, will be Y dash, and it will lie within epsilon distance to Y. Okay, please replay the thing. Okay, replay the last few minutes and try to understand and pause, review, proceed. Or you can also look at as I said the other videos, where I will take little more time to explain this thing. So let me go to the definition. What does the definition says? The definition says, okay, F is from a metric space XD or as AD. A is a subset of X to YD. Okay, fix a point X in A. I say F is continuous at A. Continuous at X, sorry. Okay, continuous at A, let us say continuous at A. If what has happened? So this is my X and this is my A. This is my A, this is my A, and this is my Y. Okay, so let us look at F of A. This is F of A. Okay, this is what I want. So what I do is I choose an epsilon interval. If for every epsilon greater than 0, that means I am forming an open ball of radius epsilon centered at F of A. Right? Then what do I want to do? I want to say there exists a delta positive, so that, okay, for every x in A, so the distance between x and A is less than delta. This is same as saying for every x in B, A delta, right? This is same as this is, what does it mean? This means x lies in A intersection Bx of A delta. You understand this? Open balls you have seen. So this is my A, then I may take, let us say this is A, this may be my delta thing. So I take only these points. Okay, there such that what happens for every x in A intersection Bx delta, which is same as Bax delta, Baa delta, what should happen? Fx lies in the open interval, open ball, Ba Fa epsilon. This is same as saying for every x in A, distance between x and A less than delta implies distance between Fa and Fx is less than epsilon. Okay, pause, review, proceed. This is what we just observed in this example here. Okay, the scientific process should produce Fa, but I may not be sure about that, so I allow epsilon error. So anything which is close to f of A, I will accept it within epsilon distance. Then what do I know? I have to control the input. The input should be within delta distance to A. Then whatever I produce with that ingredient, I will get some output which will be very close to f of A. Okay. Now what we want to prove is these two definitions are equivalent. So I have already one definition of continuity, namely sequential definition. And now I have another definition of continuity which uses epsilon delta. What we want to prove is, as I call this as definition 2, and our definition 1 is sequential definition. Okay. For every sequence xn in A, so that xn converges to A, xn converges to A, we have fxn converges to Fa. That was our first definition. So I want to say the theorem is definition 1 and definition 2 are equivalent. Right? If I assume f is continuous according to definition 1, then it has to be continuous according to definition 2, and conversely. Yeah? Proof is easy. Let us look at that. Let us assume, okay, f from, let me assume xd instead of a, OD. Okay, if you want, let us do that so that you don't get confused, and fix a point a in the, assume f is continuous at a according to definition 2, that is epsilon delta. Right? What is that I have to prove? I have to prove whether f is continuous according to definition 1. Right? So to prove that, what I have to do? So you are going to give me a sequence xn where in A, because the domain of f is A. And what should happen to the sequence? It should converge to A. Then what is that I want to conclude? I want to conclude fxn converge to Fa. Right? How do I prove fxn converge to Fa? Okay. To prove that, what should I do? What should I do? Okay, let epsilon positive be given. Then what should I do? I want to find whether there is a natural number n, so that for every k greater than or equal to n, distance between fxn and fa is less than epsilon. This all I have to check. Right? You understand that? So what is given to me? To prove the convergence of fxn to fa, I am given epsilon positive. Right? Now what should you do? Your brain should trigger. What is our assumption now? F is continuous according to epsilon delta. So now I got an epsilon. So now I know. Okay, I am full of action. What do you think I will do? This epsilon, for this epsilon, I know there is a delta. Right? Since F is continuous at A according to epsilon delta definition, okay, there is a delta positive, so that what happens? For every x in A, so that distance between x and A is less than delta, should imply distance between fxa and fa is less than epsilon. Yeah? Do you accept it? Okay. Now, so I found a delta. So let us look at the picture. So this is my delta. This is my A. This is a delta. So whenever x is here, then this is my fa. This is my epsilon. Then I know fx should lie here somewhere here in this epsilon neighbor, right? Okay. Now what is hypothesis? I want to prove f is continuous according to definition 1. Therefore, what did you give me? You give me a sequence xn and a with what property? Xn converges to a. Right? Since xn converges to a, now you have a delta ball around a. What do you know? Since xn converges to a and there is a delta ball around this, so immediately what will I know? Since xn converges to a, okay, there exists a capital N natural number, so that for every k greater than or equal to n, xk lies in the open ball BA delta. Do you accept it? Because of convergence. Yeah, this is same as saying distance between xk and a is less than delta. Okay, right. Now, yeah, therefore, for k greater than or equal to n, xk lies here. So therefore, what does it mean? So because of this hypothesis, this means therefore fxk, because whenever x satisfies this property, distance between fx and fa is less than epsilon. Therefore, distance between fx and fa is less than epsilon. For which k? For every k greater than or equal to n. You understood that? So do you think I have proved this? Yes. Yeah. Therefore, what I have proved? F continuous at A according to definition 2 implies F is continuous according to definition 1. Okay. Pause. Review. Proceed. Now let's prove the converse. What is the converse? F is continuous at A according to definition 1, that is sequential. Sequential definition. Okay. So I want to prove F is continuous at A according to definition 2. What does that mean? So you are going to give me an epsilon positive. Okay. For every epsilon positive, I have to find a delta positive. So that x belongs to A and distance between x and A less than delta should imply a distance between fx and fa should be less than epsilon. Right? This is a question mark. I do not know. So the way to prove that is assume it's false. So we will prove this by contradiction. What does that mean? For every epsilon, something must be true, right? So that is false. What does it mean? That means there is a epsilon positive, so that this is not true. If this is not true, what does it mean? I should be able to find at least one delta, so that something must be true. That means no matter what delta you give me, for every delta positive, okay, so this must happen, that will fail. That is, there for every x in A, distance between x and A less than delta, something must happen. That is true. That means there is an x where in A intersection B, A delta. Yeah, x, right? This should happen. This is false. That means distance between fx and fa is greater than or equal to epsilon. Do you understand this? Okay. It's unfortunate. Okay. People should learn how to negate a statement. Okay. This is usually done in MTTS, and you should look at our book on foundations. And sometime sooner or later, I will also produce videos on that. Okay. The way to do that. So for every epsilon positive, something happens. There exists a delta positive, so that for which for every x in A intersection BA delta, okay, distance between fx and fa is less than epsilon. Okay, right? So this is the statement I want to prove. If it is false, that is false. That is you are negating. When you want to negate, what do? You start with this. For every epsilon, something must be true. That is false. That means there exists some epsilon for which this is false. Now let's look at that. There for some delta something must be true. That is false. That means what? For every delta, okay, this is false. If this is false, what does it mean? For every x, somewhere something must happen. That is false. That means there is an x here. Okay, and this is false. Distance between fx and fa is less than epsilon. That's false, meaning distance between fx and fa is greater than or equal to epsilon. This is a negation. Okay, please pay attention. If this is the first time you are looking at a very serious such things, please pause, review, and proceed. But if you have gone through my lectures on real analysis, sequences, etc., you will find this way of thinking becomes very natural and easy for you. Because sometimes people don't do that. Anyway, I have passed real analysis. Okay, now I want to do metric space in the 6th semester, so I will only concentrate on metric spaces. Then you will have problem. So even if that be the case, please go visit my videos on real analysis. Anyway, is that clear? Now to come back, what do you want to prove? It is given f is continuous at A according to sequential definition. I want to prove it's continuous according to epsilon delta definition. Therefore, if I want to prove it by contradiction, that means what? There exists some epsilon so that for every delta something is wrong. Remember, I want to arrive at a contradiction, right? Proof by contradiction meaning I should arrive at a contradiction. So what should I contradict? Now hypothesis says f is continuous according to definition 1. That means sequential definition. So if I want to contradict this, I should show f is not continuous according to definition 1. If I want to show f is not continuous according to definition 1, what does it mean? If it is continuous at A, what does it mean? For every sequence xn, something is true. Therefore, if I want to show it's not continuous at A, what should I show? I have to find a sequence xn in the set A so that xn converges to A, but fxn does not converge to fa. Is that clear? Okay, please think. Thinking logically makes life easy. Okay, don't learn by heart or simply accept what I'm saying, right? Therefore, to arrive at a contradiction, what is the plan? Plan is to create a sequence, create or find a sequence xn, where in A, with what property? Xn converges to A. So that what happens? But fxn, so that but fxn does not converge to fa. If I have done that, then it contradicts f is continuous according to definition 1. Do you understand that? Good. So how do I find it? That is where you have to understand what I said. Okay, let's come back. So you have given me an epsilon for which the whole thing is failing, right? Therefore, for every delta positive, not greater than or equal to 0, this is positive, something is false. Therefore, if I take delta equal to 1 upon n, what do I know? There is this an x in A intersection BA 1 upon n. That n x, I will call it xn. There exists xn in where B A 1 upon n intersection A. So that what fxn and fa is greater than or equal to epsilon. Do you understand this? Okay. Right. Now let's look at the sequence. Where is the sequence? Xn's are in A. Therefore, it is a sequence in A. And what do I know? Xn's are orbital elements in BA 1 upon n. What we have observed earlier, then Xn converges to A. Right? Okay. Since F is continuous according to definition, what should happen? Fxn should converge to Fa. Right? That means distance between Fxn and Fa must go to 0. But it is always greater than or equal to epsilon. So there is no way it can go to 0. Do you understand this? For every n, distance between Fx and Fa is greater than or equal to 0. But, okay, by definition 1 continuity, Fxn must converge to Fa. And this is the same as saying distance between Fx and Fa must go to 0. But it cannot go to 0 because this number is always greater than or equal to epsilon. So it's like this, right? 0, epsilon, and all your numbers are here. So it cannot go to 0. Do you understand this proof? So our assumption is wrong. That this, therefore, F is continuous according to definition 2. Okay, pause, review, proceed. Okay, please go through that. Yeah, okay. In the next lecture, we will do in terms of open sets, etc. Okay, so for the time being, let us have a break. If necessary, we'll resume later. Please go through the proof. The proof is easy. Okay, I have taken a lot of pains to explain that. Feel confident. And the one thing which you have to observe is the negation of statements. When you want to prove a contradiction, you are making a statement and you want to say, you want to prove that. If you want to prove a contradiction, you have to say that statement is false. That means you have to negate it. Many students do not know how to do that. Teachers also don't take pain to explain that. Okay, I have done it in my just now, and please also visit some of my lectures and analysis. Okay, right? Just don't assume I had already done analysis. I have passed it. I got a good grade, so I don't need to revise that. Please don't do that. Okay, please go through it. Learn anything thoroughly. So now what we plan to do? What we plan to do is that so far you can see we use metric notions. What does that mean? To prove, to define continuity of F, even sequential definition, we wanted to say if xn converges to x, that means d of xn x a goes to 0, then d of fxn fa goes to 0. If xn converges to a, fxn converges to fa. And the next one is epsilon-delta. That also it said you form an epsilon ball around fa, then I can find a delta ball around a, so that f maps the open ball ba delta inside the open ball bfa epsilon. See that? See, in both the definitions, we had the metric notions. The notion of metric was crucially used. What we want to do is we want to investigate, okay, can we replace this by means of open sets? Okay, but remember in the metric space, even open sets, we define using metric. Okay, but then we saw the so-called collection of open sets form a topology with certain properties. So if you can characterize continuity in terms of open sets, we can generalize the notion of continuity to sets which are not necessarily metric spaces, something larger. Okay, it may look abstract, but don't worry. If you follow, it's fine, because some of you might have already heard something about topology, etc. So it might help you, but that's not at all necessary. Let's go ahead. Okay, so let's start do that. So what is the question I want to look at? The question I want to look at, I have to share the screen. Yeah. Okay. So what we want to do? What we want to do is, can we characterize? Okay. Can we characterize continuity at a point of a function? Okay. In terms of open sets. Okay, where X and Y are of course metric spaces. Okay, so let us look at. So let us look at the epsilon delta definition. What did it say? So if F is continuous at A, okay, you started with an open ball B of A epsilon, right? For every given epsilon, I have an open ball. Then what did I find? There exists a delta so that I have an open ball F B A delta. So that what happens? If X belongs to this implies Fx belongs to this. That is F of B A delta is contained in B F A epsilon. So in terms of pictures, this is my X, this is my A, this is an open ball, okay. This is my Y, this is an open ball, okay. This is FA, okay. This is X, A, then this is epsilon. So what did I know? I can find an open ball B A delta, this is delta, so that for every X here, the image Fx lies here. That's what it said. Yeah, okay. Now let us look at it a little more carefully. We had already seen any open ball in any metric space is an open set. Therefore, the open ball B FA epsilon is an open ball in Y. That's an open set, right? Then what did we say? There exists a delta positive. Therefore there is an open ball B A delta. That means there is an open set. Okay. Now what is the speciality of the open set B FA epsilon? Is that it's an open set containing F of A. And what do you have information about B A delta? It's an open set containing A. So what does it suggest? It suggests that if V is an open set in Y containing FA, I should be able to find an open set U in X such that for every X in U, Fx belong to V. Okay. Just keep you focus. Let me just say that I will write it so that you will feel happy that okay, because some of you will have problem with uh, attention, right? Because so in terms of open, so suppose I take V equal to B FA epsilon. So this is an open set, okay, containing FA. Now let's look at U. This is B A delta. This is also an open set containing A. So what have we shown? If F is continuous at A, okay, given B an open set containing FA, there exists U an open set containing A, so that Fu is contained in B. That is same as saying for every X in U, Fx belong to B. You see that? So we have, okay, right? So for this B and U only we have proved. So what we want to do is we want to see will this work? Okay, definition 3 in terms of open sets. Okay, I don't know whether it's going to be definition 3. Okay, we don't know that. Okay, so let you have from X to Y. If you want again A, okay, let A be a point in X. So I want to know, I say F is continuous at A if for every open set V in Y so that FA belong to V, there exists an open set U contained in X so that A belong to U and Fu is contained in V. That is for all X in U, Fx belong to V. See, now there is nothing like, suppose you forget about the metric, okay, we got a metric Using the metric, we got the collection of open sets. Now you can see this definition. Suppose you have the collection of open sets in X and the collection of open sets in Y, then I don't need epsilon delta, I don't need metric. Assuming this is a correct definition, that we still do not know. Okay. So what does it say? F is continuous at A. That means look at the same picture. Now instead of this, don't think of this as an open ball. Think of this as an open set containing FA. I have an open set containing A, so that for every X in this open set U, Fx belongs to this B. Right? Okay. Please pause, review, proceed. Right. Okay. So what we want to prove? Now we want to prove definition 3 and definition 2 are equivalent. If you want, call it as a theorem. What is the definition 3? That is in terms of open sets. What is the definition 2? In terms of epsilon delta. We want to prove. Once I prove that, assuming this is true, what do we know? Definition 2 is equivalent to definition 1. Therefore, definition 1, definition 2, definition 3 are all equivalent statements. Isn't it great? Okay. Right. For the definition 3 to make sense, what do we need? I do not have to know how the open sets are obtained. The fact that there is a class of open sets, that's good enough for me to make this. Okay. Don't worry about it. Let's go through the proof. Okay. So what do you want? Let's assume definition 2. I want to know whether it implies definition 3. What does it mean? It means that f is a function of x to y, a is a point in x, and assume f is continuous at a. At a, according to definition 2. So I have to prove f is continuous according to definition 3. So what does that mean? So f continuous at a according to definition 3. So if I want to prove f is continuous at a according to 3, what should I do? You are going to give me an open set V, so that f of a belongs to V. You understand that? So you have, okay, this is my y, this is my V, this is my fa. Okay, and this is my x. So this is my a. Okay, this is my fa. Now what I have to do? This is my f. I have to find an open set here, right? How will I do that? Remember, I just have to find an open set U containing A, right? How will I do that? Now I have to see, now you see, to prove this equivalence, we are working in a metric space. So I have to say this V is open in the metric space Y containing FA. Okay, so V is open and FA belong to V. What does this mean? That means there exists an R positive, but I will write it epsilon positive so that there is an open ball BA epsilon which is completely contained in B. Do you understand this? Because this is open in the metric space, right? Okay. Now I'm happy. Why I'm happy? Because F is continuous according to which definition? Epsilon delta definition. And you gave me an epsilon in the codomain. So what do I know? I know that there exists, yeah, delta. So this is my delta, right? Since F is continuous, F continuous at A according to epsilon delta. So for this epsilon, there is a delta positive, so that for all x in BA delta, what do I have? Fx lies in B, Fa, epsilon. That is, and hence in particular it belongs to B. You understand this? Now what is the open set I'm going to construct now? U must be an open set which contains A, so that for every x in U, Fx must lie in U. So what is the obvious choice of U for me? Yes. Okay, therefore take U equal to B, A delta. Then we have proved it. For every x in U, Fx belong to B. Fx actually belong to BA FA epsilon, but then BA epsilon is contained in U. Okay, this is an open set which contains this. This is my B FA epsilon, right? So every point here, I go here. That's it, right? So what have we proved? We have proved if I assume F is continuous according to definition 2, it is continuous according to definition 3. Okay, pause, review, proceed. Now let's look for the converse. So let F be continuous at A, okay, according to definition 3. So I have to prove it's continuous according to definition 2. This is what I have to prove. Right? What does that mean? It means that to prove F is continuous according to definition 2 is an epsilon delta definition. Therefore, to prove F is continuous at A, so I am given epsilon positive. Then I have to find a delta positive such that something happens. Let's not worry about it. We'll think about it later. You understand that? Okay. So let's look at the picture. I have to keep drawing the picture, same picture. It will be easier if you can imagine. So this is your FA. Okay, epsilon is given. Therefore, I found an open ball. Okay. Now let us look at this. Okay. So naturally, is given epsilon. Okay. I can form the open ball BFA epsilon. You understand that? Very good. Now let's look at. I have to make use of continuity of F according to definition 3. Definition 3, what does it say? It says that give me an open set B which contains FA, then something happens. Right? I can find an open set U containing A such that F of U is contained in V. Right? So to you exploit the hypothesis, namely F is continuous at A according to definition 3, what should I do? I have to find an open set B containing FA. What is the obvious choice? Yes. Take B equal to, let B equal to B FA epsilon. This is an open ball in B, in Y, therefore this is open. And it also contains FA by very definition, right? Very good. Therefore, what do I know? Since F is continuous at A, according to definition 3, there exists U in X which is open and A belong to U, so that for all X in U, Fx belong to B. This is our hypothesis, right? Now A belong to U and U is open. So what do I know? I know that there is a delta positive. Usually I will write it as R, but in this case, since I am working with epsilon delta, I am writing. Okay, so that BA delta is contained in U, right? But then take X in BA delta, right? What happens? This is contained in U, therefore X belong to U, but then for every X in U, Fx belong to V, this is V. Okay, this implies Fx belong to V, but V is B Fa epsilon. So what I have shown that for given epsilon positive, there is a delta positive, so that for all X in BA delta, Fx belong to B Fa epsilon. That is for all X, so that distance between X and A less than delta implies distance between Fx and Fa less than epsilon. So that means if F is continuous at A according to definition 3, we have proved it's continuous according to definition 2. Okay, pause, review, proceed. Okay, so what you have shown is now we had successfully carried out a program. what is the program? We started with the continuity of f at the point in terms of sequences. Next, we defined continuity of f at a in terms of epsilon delta. Next, we defined continuity of f at a in terms of open sets v and u, v in y, u in x with certain property. And we have proved these three are equivalent. How did you prove? We proved 1 is equivalent to 2, definition 1 is equivalent to definition 2, and we proved definition 2 is equivalent to definition 3. Therefore, all three are equivalent statement. Okay. This is now what have you done? So far, we looked at only continuity at a point, right? But we already know what is meant by continuous. Okay. Now, our next goal is something else. Suppose f from x to y is continuous on x. What does that mean? This is the same as, by definition, the same as saying f is continuous at a in x for every a in x. Okay. This we already made in our first or second lecture, right? Okay. So my natural question is, okay, can I define continuity of f purely again? I want to say f is continuous from x to y if and only if in terms of open sets. You understand the problem? It's not a continuity at a point, but I want to prove it more general statement. Okay. So question is characterize or aim. Characterize continuity of f on x in terms of open sets. We do not know what it means. We just have to explore. Do you understand this? Right. Okay. Because usually these kind of things are not done in detail. Okay. They immediately jump to continuity on all of x, but it's important to understand continuity at a point and the equivalent conditions. That's what we are done. Okay. Now we want to do that. Okay. So due to time constraint, I will not be able to complete this, but we will get started. Okay. Suppose f from x to y is continuous on x. Now, what does it mean? F is continuous at each and every point a in x. According to which definition? Now I don't care any one of the three definitions because all are equivalent. So that doesn't matter. But for the, since I want to do in terms of open sets, I will concentrate in according to definition 3. Do you follow that? All are equivalent, so I can use any one of them. Okay, but I'm going, since I want to characterize continuity of f on the whole set x in terms of open sets, I want to work with the definition 3 possibly. This is my idea, I do not know. Okay, right. So let us say according to definition 3, but it's strictly not needed. They are all equivalent. Okay, right. Now suppose you give an open set. Now you see that this is an open set. Now there is nothing a, no f, nothing. Just as v is an open set. Yeah. Now the play. Okay, we are going to play with this now. What are we going to play? Okay, start with a y. Okay, let us call a y in v. Now, right? Suppose y is in v. There are two possibilities. Okay, the possibilities there may exist an x in x so that fx equal to y, or y is not in the image. Right? So this is my thing. My f of x may be this. This may be the image. My y may be here. This may be y. This is my x. This is my f. Right? This may be my f of x. Y may be here in that case. You understand that? Right. Okay. Right. Suppose this case we will not worry about for the timing. Let us concentrate on this case. Suppose there is an x that fx equal to y. So let us fix an x. So my x is going to be not here. My y is going to be here. So let it give me a color so that you will know this is my y, and there exists at least one x. There may be more. You understand that? Yep, need not be one. There may be x1, x2, xn. Okay, or may infinitely many points which may go to y. For example, if f is a constant function and y is the constant, then entire x will be going to y only. You understand that? But at least there is one x. Are you following? Okay. Now, what do I know? What I have is fx equal to y. Since fx is equal to y and f is continuous on x, what is our definition of continuous on x? It is continuous at each and every point. Therefore, f is continuous at x. You understand? F is continuous on x. That means f is continuous at x in particular, right? Since f is continuous at x and we chose to work with the definition 3, so what will I do? Okay, there exists an open set. You call it ux, right? In x, so that x belongs to ux, and for every z in ux, fz belongs to v. Why? Why is that possible? Try to understand. My y is where? In v. Therefore, v and v is open. And what is our definition of continuity according to definition 3? F is continuous at x if for every v in y such that fx belongs to v. You understand that? And my y is fx that belongs to v. And x is continuous, therefore there is an open set. Are you following? Please go back and understand. Okay, don't assume. This is because of definition 3. Right? Very good. Now, you follow that? Very good. So now let us look at the set of all x in capital X so that fx belong to v. Okay, that's the condition we are looking at, right? I'm not claiming every point of v is in the image of x, image of f. I'm not claiming. It may or may not happen. You follow that? Okay. Now what? Call this set as u. Right? So this my u may be something like this. This is my u. Okay, what does it mean? Every point here, its image will lie in v. Okay, so my v may be, okay, maybe it's also a good picture to have my v. This is my fx, my v may be like this. This may be my v. And y happens to be there, or y may not also be there in f of x. Do you understand this? Yeah, v is an open set, and this is the image. So I'm starting with the y, which is in v, which is also in the it's also in the image. Or I may take a y which is here. In that case, there is no pre-image. Okay. Let's look at the set. What can you say about the set? Remember, u is a subset of x. What can you say about u? Notice that for each x in u, what we found? Fx belong to v. Therefore, that is your y. Right? Therefore, what I know is, please pay attention. This is not the same x there. This is any arbitrary x in u. Let us look at fx. Call this as y equal to fx that belong to v. Right? And therefore, v is an open set containing fx. Therefore, there is an open set ux containing x so that f of ux is contained in v. You understand this? Sure? That means what? This is contained in v. Yeah? Therefore, each x there exists an open set ux. Where? In x. With what property? F of ux is contained in v. That is, for every z in ux, fz is in v. Okay. So now next question. What is the relation between ux and u? Start with any z in ux. What did I say? Fz belong to v. Okay, that means this implies Z is in U. That means Ux is contained in U. And what is Ux? This is an open set, right? Now let's look at U and the union Ux, and X varies over the set U. For each X in U, I have a Ux, right? So I look at this. So what's the relation? Now remember, each Ux is contained in U, therefore the union is contained in U. And if you give me an X in U, then that X belongs to Ux, therefore X belongs to the union, therefore this is contained. Therefore, what I have shown is union Ux, X in U is nothing other than U. But these are all open sets. So what is it? U is not union of arbitrary union of U is the union of open sets. Open sets Ux, and this collection varies over U. So come back. What do you think I have proved? So let us go back, understand slowly. So f is a continuous function from x to y. It is continuous on all of x. Okay, that means it's continuous at each and every x in capital X. And the definition is we are using definition of continuity in terms of open sets, that is according to definition 3. Then what did you conclude? You start with any arbitrary open set V in Y, and let us look at the set of all X. Okay, and said that fx belong to V. As I said, for any given Y, there may be many X. I don't care. So collect all such X so that fx lie in this V. You understand that? So what have you proved? The set U is open. So let me formulate as a lemma. Okay, f from x to y continuous on x. Then if V is in Y is open, then the set U, which is defined to be set of all pre-images, fx belong to V, is open in X. Okay, pause, review, proceed. We have proved that if f from x to y is continuous on x, then start with any open set V in Y, the set of all points x in X, so that fx belong to V. That call it as U, that is open. So what is the next question you can ask? Yes, the converse. What is the converse? If U is an open set in Y, so that define U the way we did. If V is an open set in Y, define U to be set of all x in X, so that fx belong to V. Then U is a subset of X. Okay. Now let me assume the function f has the following property. That is, for every set V open in Y, the corresponding set U as we define is open in X. Can I conclude f is continuous on all of X? Do you understand that? Okay. So we will take up this, and also we will formulate in terms of closed sets in the next lecture. Okay. Right.